We're looking at inverse functions here. A couple of things notationally we'll address first is that if we have a traditional function, we call it f of x, okay? It just stands for y. It's just another way that we write equations that belong in the function category, okay? And when you have a function that reverses the operations of an original function, then we have an inverse function. So it's easier to think about it like this. Suppose we do the inside stuff first, okay? Suppose you have this f of x function, and let's suppose it's adding 3. Then the inverse function comes along. It takes whatever you output and it reverses it. So it'll take whatever you have and it'll subtract 3. So it will basically negate what the original function did and take you back to where you started, okay? Now, notationally, this notation, the power of -1, people think of as a fraction, and I'll tell you right now, it is not, hence the not equal to here. It is not a fraction, and here's the difference. When you see something like 5 times 2 to the -1, this is on a number. So this does mean it should be in the denominator of a fraction. So it should be 2 to the 1 in the denominator. That exponent is on a number. When it is on a function, it means inverse. It does not mean fraction. So when it's on a number, it means fraction. When it's on a function, it means inverse, not fraction. Okay, so there lies the difference. Some examples here. If I have a function and when 2 is plugged into the function, 4 comes out, the easiest way to do this might be, say, x is what goes in and f of x is what comes out. So f of 2, so 2 goes in and out comes a 4. So who knows what the function is, whatever the function operation is, in goes 2, out goes 4, okay? And for the next one here, in goes 5, out comes 12, okay? When we are working with the inverse function, it does a mapping back. So the inputs for the inverse, suppose 4 went in, right? And I should be careful here how I write this. Our values that go in, and then the inverse will spit out a value, okay? So if I put 4 into the inverse function, 2 will come out. If I put 12 into the inverse function, 5 will come out, okay? So I could say, or write them as coordinate points, right? Original function, 2 goes in, 4 comes out. 5 goes in, 12 goes out. Inverse function will reverse what the original function did. So in goes 4, out comes 2. In goes 12, out comes 5. All right? Now, here's a notable for this. This is the domain of the original function. So I'll write domain of f of x. When you have an inverse function, right, a function has an inverse, the domain of the function will be the same as the range of the inverse, okay? And likewise, the range of the original function is the same as the domain of inverse. Okay? All right. Yeah, I scribbled a lot. Now, looking at number 2 here, to show that a function and, or rather 2 functions are inverses of each other, we are going to take the composite one way, takes in x, does the operations, and then the inverse comes along, reverses all the operations, and you're left with x. And the composite has to work both ways. So the composite where the inverse is inputted into the original function also has to end as a result of x, or results in x. Okay, so when I do that here with g and f, I have to show that g of f of x equals x. This is something I have to show. You can't just say it, we have to show it, okay? I also have to do the other composite. So I have to take the f function and I have to plug the g function into it. Okay, so I got to do both ways. So first things first, I'm going to take the g function, which is 1 over x minus 2. And in that x spot, I'm going to put the entire f of x function. So it will look like 1 over x plus 2, and then a minus 2 after that. Holy smokes. Well, if I have a fraction divided by a fraction, I multiply by the reciprocal. So this part will end up being x plus 2 minus 2, and we did get it to equal x. So this one is done. Now let's do the composite the other way. I'm going to take the f of x function, which is 1 over x plus 2, okay? And in that x spot, I'm going to put the entire g of x function. So 1 over x minus 2, and then I have the plus 2 on the back end of that. Well, these are gone. And I now have 1 over x. We'll multiply by the reciprocal. This is x, so I have shown it this way as well. I have shown it both ways. So I'm going to summarize and say, since f of g of x is equivalent to g of f of x, which is equivalent to x, they are inverses of each other. Okay? All right. Let's move on to example 3 here, which is, suppose we have this function f of x, which is x cubed, and g of x, which is 1/3 x. Is g, the function for g, an inverse function for f? All right, there's 2 different ways to do this. One is if they are inverses. So let's test it. Suppose yes. Okay, if it is, then f of x plugged into g should be x. And this will be a true statement if they're inverses. So I'm going to take my g function, which is 1/3, and in the x spot, I'm going to put the f of x function. Does this equal x? No. So is g an inverse? G is not an inverse of f. All right, domain and range of functions and their inverses. We've already talked about the domain and the range. Remember when I showed you with the table and with the coordinate points, first example? Okay, so here we kind of just rehashed that. Whatever was in the original function will be equivalent to what comes out of the inverse because they negate each other. So let's jump to number 4 here. A function f of t, shown in the table, okay, shows the distance in miles that a car travels in t minutes. Find and interpret f inverse of 70. Okay, so regular f function inputs time, outputs distance. So the inverse function is going to input distance and output time. Well, if we have f inverse of 70 equals, so 70 in this case is distance. It outputs 90, right? So it says interpret. For a distance of 70 miles, the car traveled for 90 minutes. All right, let's go to graphs of functions and their inverses. Well, graphs of functions, I'm pretty confident that you should be fluent in making tables of values and graphing. Now, for this particular example, they just have the graph of the original function. So this is g of x in blue, okay? Remember, we have x goes in, and g of x was the y values coming out. So for these values, let's see, we have I'm just going to approximate these values, okay? So, actually, let's do this one. If x is 3, then g produces a 1. So 3, 1 is the coordinate point on the g function. So x and g inverse. Okay, so because we know domain and range flip-flop, when a 1 goes in for x, the inverse function produces a 3. Okay, so if the function has a 0.31, the inverse has a 0.13. Right there. I'm going to go one step farther, and I am going to graph the entire inverse function, even though it's not asking me that, okay? Oh, I didn't answer this question yet. This one says, what do we get if 3 goes in? I answered this question. I did not answer this question. Okay, well, how do we find it? Well, let's go back to the original problem. This is not what it was asking. It was asking for this one. Let's see, if it's the input for the inverse, and then it's the output for the original. So when does the original function have a value of 3? Well, that's here, 5, 3. So that means in the inverse, it's going to be 3, 5. Okay? So, actually, I'll do this in a different color. This one was the yellow part. G of 3 is a 1. And the second part was G inverse of 3. And we decided now that that is 5. All right, so 5, 3, and then 3, 5. This is going to be the graph of our inverse function. And I'll slow down a little bit. All right. Whether you know it or not, chances are you've already worked with inverse functions. You just never called it that before. So right here is the equation that we would use to take a value in Fahrenheit and convert it to the equivalent in Celsius. Okay, so if I plugged in 32 degrees for Fahrenheit, that would be equal to 0 degrees Celsius. Right? So what they're asking us to do is find the inverse function. So in other words, if you had Celsius and wanted to convert to Fahrenheit, how would you do this? So what they're asking for is, what would F be if you knew Celsius? So basically, we're just going to solve for the other variable. Okay, so multiply both sides by 9/5 and add 32. So in other words, if you know the Celsius and you want to convert it to Fahrenheit, you would do this math. Okay? A function's inverse. One, make sure it's a one-to-one function, because if it's not one-to-one, it doesn't have an inverse. Okay? This one is, we in a previous section looked at identifying functions and then identifying whether a function was one-to-one with a horizontal line test. Okay, so search back if you're looking for that information. Okay. This is, if I grabbed a calculator, we would see, and I don't want to focus on what the graph looks like right now. I want to focus on the process for finding the equation of the inverse. So the steps are, because our inputs and our outputs flip-flop, we are going to interchange the x's and the y's. So this part is going to be 2 over y minus 3 plus 4. Now, this is normally how we write our function, or that's how we would equate it to the y value. So when we change that, it's going to go to x. Okay? Now, I'm going to solve this for my new y. So that's number 3 here, step. Okay, so first things first, I'm going to subtract 4. Okay. I don't like working with fractions. Most people don't. So I'll multiply both sides by y minus 3. I'm going to divide the x minus 4 off. And now I'm going to add 3 so that I'm solving for my new y value. So 2 over x minus 4, and then after that plus 3. So this is my inverse. So you know how f of x is what our original function was called? Well, this is the inverse. And x is the input, so we can notate it that way. And there's my inverse function. Okay. Now, I know we've already visited about domain and range, but a couple of notables. This original function, the domain of this original function is that x can be anything except 3, because we would have a denominator of 0, and that's bad. Okay, and I'm going to skip up the range for now. I'm going to come to this one. We know that the domain and the range are going to flip-flop. So I know the domain of f, so that means I know the range. I can say y, or I can say f inverse values are going to be all values except, I'm going to say y, actually. It'll be easier for right now. Except for when y is 3. And we know that because the domain and the range flip-flop. Now, I'm going to go one step further and say, what about the domain of the inverse, right? So let's go to the inverse function. I can see that I cannot have x be 4, because that would give me a denominator of 0, which is bad, okay? And undefined. So I'm going to go back up. If that's the domain of the inverse, then it is equivalent to the range of the original, the set of y values, such that y is not 4, like so. Okay? All right. Let's keep going here. Find the inverse of this function. So we're going to follow the same steps. This graph is one-to-one. Okay? We're going to graph. I'm going to graph down here. So I'm not going to focus on the graph piece. I'm going to focus on the steps. Okay? So one-to-one, check. 2. We're going to interchange our x's and our y's. So this is going to look like x equals 2 plus the square root of y minus 4. And step 3 is to solve for your new y value. So I'm going to subtract 2 square each side. This presents a problem. All right, and then y minus 4. And then add 4. And I shouldn't say it presents a problem drastically. It's just we need to have a conversation about domain and range. Okay? So this is my inverse function. So instead of y, I'm going to call it f inverse. So my f inverse is the quantity x minus 2 squared plus 4. Now, this is a quadratic. If we graphed this, we are going to have a quadratic. That's not 1-to-1. So that's not good. Okay? So we need to definitely state some things about the domain and the range. Let's go to the original problem again. Underneath a radical, we can't have a negative or an even radical, right? So a square root. So x minus 4 has to be greater than or equal to 0, which means x has to be greater than or equal to 4. Okay? That is the domain of the original function. Okay? And maybe I'll do interval notation. Say domain, it can be 4 and then anything larger than it. Okay? This is for the original function. We'll come back to the range here in a second. All right. Let's go to this function now. Remember, we graphed it a minute ago. And when we graphed it, it was over 2, up 4. 1, 2, 3, 4. And it made a U shape. Well, this domain didn't really help us too much, did it? Because it's saying that the x values of the original function go from 4 to infinity. Well, that's the range of our inverse. Okay? I need to focus my attention on the domain of the inverse because that's the same as the range of the function. Okay? So let's go up here to range again. If I'm going to propose that this graph get altered and this part of it be gone. And here is why. Up here, since this 0 or larger, then what do we know about 2 plus it? Is going to be 2 or larger. So the range is anything 2 or larger. Well, that means that the domain then is 2 or larger for the inverse. So this is our inverse graphed. This is our inverse equation as long as x is greater than or equal to 2. Okay? All right. So sometimes we have to do a restriction to make sure that it stays a 1-to-1 function. All right? This original, if you graphed this original, it would look like this. 2. If it was just a 2, that would be a 4 there. So 4, 2, and it goes this way. Okay? I'm going to put f of x and f inverse of x on the same graph. The notable here is that they are reflections over a diagonal line. Another notable is this was 2, 4. This is 4, 2, right? Remember our domain and our range flip-flopping? There's a relationship there graphically as well, which is what we're addressing in this next example. We saw that there's a reflection over a diagonal line. That diagonal line is the line y equals x. So here's the line y equals x. And you'll notice that if for every data point that we have, say this one is 1, 0, well, the inverse is going to have 0, 1. This one is 2, 1. So we're going to have 1, 2 on the inverse. Okay? It looks like there's a 4, 2. So let's go 2, 4 on the inverse. It's approaching the negative y-axis. This will be approaching the negative x-axis. And there's the graph of F inverse.